Hello and welcome. My name is Cindy Heitzman, Executive Director of the California Preservation Foundation. Thank you for joining this webinar on materials conservation, wood. The format for today's webinar will include an hour presentation followed by time for questions and answers. There's a toolbar on the right side of your screen. If you have a question at any time during the presentation, please type it in the box and I will either reply to you or hold the question until the end for our panelists to answer. Please refer to the audio tab in the toolbar and select if you are listening through your telephone or speakers. To hide or unhide this toolbar, click on the orange arrow. Please adjust your volume on your computer or phone. Today's presentation will be by Janelle Leafblad with Simpson, Gupperts, and Heger. Janelle Leafblad has more than 10 years of engineering consulting experience, primarily in the area of wood durability, investigation, and design of building envelope components and construction for both historic and contemporary structures. Ms. Leafblad is a registered professional engineer in the state of California. She holds a Bachelor of Science degree in Architectural Engineering from the Milwaukee School of Engineering and a Master of Science degree in Wood Science and Technology from the University of California, Berkeley. She is a professional affiliate of the Wood Products Society, the Society of Wood Science and Technology, and the Association for Preservation Technology. She is profiled on the popular Engineer Girl website to interest middle school and high school women in the STEM professions and is featured in Ask an Engineer. Thank you for joining us today.
Thank you so much, Cindy, for welcoming me. And I just wanted to give everyone a little bit more of my background. I first became interested in wood as it relates to engineering and the built environment when I was privileged to do an internship at the USDA Forest Products Lab in Madison, Wisconsin, and really realized that this is a material that we have used right since the beginning of time, and man continues to use wood, but it's still not a very well understood material. And there aren't very many universities that even give engineers the opportunity to learn more about wood. So I've really tailored not only my education, but my practice in wood, and I'm super excited to talk to you about it today. Let's see how we get going here. So I wanted to start out with a little bit about some facts of the forestry today. And I think there's a lot of misinformation or miscommunication that revolve around forestry. It's such a hot topic, especially in the environmental community. So I just wanted to lay out some basic facts. One is that the area covered by forests in the U.S. today is approximately 72% of the forested area that existed in the 1600s. And you'll see a lot of these maps that are appearing on the right of the screen as people talk about what has happened to our forests over the years. Have we overforested? And I'd just like to point out that a lot of the information really stops at 1920. And I want to emphasize that we need to look past 1920. We learned a lot from our mistakes. And the geographic area that encompasses the U.S. today has more forest coverage than it did in 1920. And in fact, the forest growth is exceeding our harvest currently by 70%. So in fact, it's a resource that's almost underutilized. And so today we're really dealing with forestry science, and that should be guiding the restoration and management of forests. really to ensure that our raw materials are produced and used in a sustainable fashion. And then because let's go backwards, sorry. Because wood is, one of the greatest attributes of wood is that it's renewable. I really like this quote from naturallywood.com that it's a great tagline that wood is renewable by nature and sustainable by design. So it's up to us. We can certainly plant trees and continue to harvest them, and then we need to use wood in a responsible manner. And if we do that, part of that is understanding that wood can be durable, and that the durability is definitely going to depend on how it's designed and maintained. And here's two really great examples of wood that have been in service for a long time. I'm sure most of you recognize the church on the left, one of the stave churches in Norway. It was built in between 1180 and 1250. And then the Japanese temple on the right was built in 752, and then again rebuilt in 1709. Was the largest wood structure in the world. Wood can definitely be durable, and we want to understand how to do that in design. And then one of the other reasons that's just good to be knowledgeable about wood is that it's so prevalent in our built environment that it involves a lot of how we're safe walking job sites. It's really important, of course, to understand when you're on a scaffolding and you look down and realize that nothing is fastened together, or maybe things are cantilevered inappropriately, what you're looking at. So today our learning objectives are to understand more about wood durability terminology. I'm a wood scientist, so please forgive me. I get really excited about wood terminology, and I don't want to get bogged down in the scientific side of things. Let's stay on the historic conservation side of things. So we're going to review some field investigation and structural assessment techniques. We'll talk about wood preservative treatments. We'll talk about some of the common repair techniques. And then what you'll see throughout the presentation is that we're really developing along three themes. One is wood as it relates to dimensional stability and moisture movement, and another is deterioration, and the third and final theme is on conservation strategy. And we'll look at everything through macro and then micro levels, and this out and back. And it really has to do because you can't talk about wood in service without remembering that wood was once a tree. And a tree has three main functions: to conduct water, and to support the tree body, and to store biochemicals. So we'll always be going back to this organic material and how it's impacted by its origin as a living product. So I like to refer to wood as like the ultimate zombie material, right? It's wood in service. It's no longer living, but it thinks and it acts like it does. And we'll discuss some of what that means in this presentation. So to start with, some basic wood terminology. Softwoods and hardwoods, I'm sure everybody understands the difference between those two. Softwoods are what we see in the built environment primarily for our structures. They're the Douglas firs, the redwoods, the cedars that are used in construction. Hardwoods are the maples and the oaks more used in interior cabinetry and flooring. And then both of those two types of wood, softwood and hardwood, they all come from a tree, right? And so we have to talk about the tree terminology. Whether it's a Doug fir or a maple, you'll be able to determine that there's heartwood and sapwood. And that heartwood is the center of the tree, and sapwood is the outer ring. So the heartwood is storing all of those biochemicals and is really durable. And the sapwood has stores some biochemicals, but it's transitioning into that heartwood phase. And then these two areas, as the tree grows, they develop growth rings. And because I'm presenting this in the northern hemisphere, we can talk about early wood and late wood. And early wood, that beginning of the growth cycle, and then late wood, the smaller, darker band, being the end of the growth cycle. This used to be called spring wood and summer wood, but that doesn't always make sense and can be confusing. So it's important to know these two terms because they'll come up later in the presentation. And I show this slide mainly because, as I said, I'm a wood scientist, and that these kind of photographs make me really excited. I can definitely talk about the terminology behind these. But today, this picture is really just to show that wood is complicated. It's a composite material, and there's a lot going on. And even at the cellular level, a great deal of wood science happens at the cellular level because the cell walls contain those basic building blocks that can be broken down and changed by deterioration mechanisms. And we're going to talk about some of those today, specifically decay fungi and insects that really like what's hidden or being held in these wood cells. So whenever we're on a historic project, one of the first things that always comes up is, what is this wood? And especially when we're talking about softwoods, it's imperative to get a microscopic examination in order to determine species. It makes a great deal of difference for a structural engineer to know that they're dealing with Doug fir as opposed to, say, a pine. And a lot of people will like to tell you that maybe they can identify this just visually, and that may or may not be true. It's actually easier to do that with hardwoods than it is for softwoods. But it's always important to take a little sample and send it to a wood scientist or who can identify the species for you, because it'll be a good estimate of the properties for that timber, and the design and evaluation of the components are all going to depend on what species you have in service. So just as an example, these three photographs here, these are photographs under a hand lens, not even a microscope yet. You can see there's great differences in these, but they're all the same species. This is Douglas fir. So you can see how visually things are going to look different even when it's the same species. So it's important to get a look under the microscope and get some of those identification qualities, such as the spiral thickening, and we use resin canals that really give you the ID that you're looking for. And why is this so important? So I really like this particular example because you know, oaks, it looks very similar side by side, red oak and white oak, but this example right here, this cross section at the longitudinal section, is a great example of why you're going to find wine barrels made with white oak versus red oak. You see all of these pores in the red oak. All of those are wide open. So if you were to make a wine barrel out of red oak, you'd probably have wine quickly dripping out of your barrel. Whereas in white oak, all of these cells are closed. And that's a lot easier to see under the microscope than it is macroscopically. I've also seen people dip a little piece of wood into, say, a solution with soap and then blow on the end, because wood is composed like straws. And if you're blowing through the wood in the right direction, in the longitudinal direction, you can blow bubbles. Something fun to do with your kids. So let's go back to these themes of dimensional stability and moisture movement now that we've talked about some of these basic terms. So one of the really interesting features of wood as a material is its hygroscopic nature. And wood is always seeking to be in equilibrium with the air that surrounds it. So basically, wood is always going to be gaining or losing moisture as a function of temperature and relative humidity. So as the wood gains moisture, the wood swells. And as the wood loses moisture, it's going to shrink. But it only does that until it reaches a certain moisture content. And that moisture content is known as fiber saturation, the fiber saturation point. So basically, the wood is gaining moisture as it's saturating its cell walls. And then once the walls are fully saturated, then the cell lumens start filling up. And that's the point of full wall saturation. Right before the lumens start filling up is called the fiber saturation point. And it's kind of a mystical number. It's hard to duplicate even in the lab. But right at the fiber saturation point and above, there's no more shrinkage and swelling. And so for most species, the fiber saturation point is around 30% moisture content. And just consider that in terms of, say, an average moisture content for interior wood is around 6 to 11%, depending on where it is. So wood in service is always going to be subject to shrinkage and swelling. And the other main point is that wood is orthotropic, meaning that it's unique and independent of mechanical properties in three different directions. And so what does this mean to us? In the longitudinal, radial, and tangential directions, we're going to see differences in shrinkage or swelling. And this little graphic on the left from the Wood Handbook is showing that where you cut your timber from a log is going to change how it reacts to the shrinking and swelling of the hygroscopic nature. It's going to react orthotropically. So you could have greater shrinkage tangentially than you will, say, radially. And from a historic perspective, this means a lot, because if you've taken a building or something that has really high-end wood flooring, say, out of service for a great deal of time, and then maybe you're bringing it back online, if you don't control the environment very carefully and very slowly, the wood seeking that equilibrium point is going to move too quickly, shrinking or swelling. And you might see buckling or twisting or warping. Thinking here. So we've covered some of this basic terminology. And just to remind you, wood moisture content is really describing the amount of water contained in wood. And when we talk about, in terms of wood science, when we talk about green wood, instead of talking about the sustainability aspect of wood, what we're really referring to is that wood that's been taken right out of the forest is going to have a lot more water in it than it's going to want to see in equilibrium, right? So say you've just cut down a Doug fir, the sapwood could be at 115% moisture content, and the heartwood could be at 37% moisture content, but it's going to equilibrate to around, hopefully in service, to around 12 to 13%. So that reduction in moisture content is going to cause a lot of changes, like we've talked about in the wood, in those three directions. And we've covered a little bit about the fiber saturation already. So because electrical properties of wood depend so much on the moisture content, and the electrical properties change greatly with little changes in the moisture content, of course, below the fiber saturation point. We've spent a long time using electrical measurements to accurately predict moisture content. And so one of the ways that we do this quickly and easily in service is to use a moisture meter. And here's a little show and tell on some basic facts about moisture meters that are really easy to use. Here shown as some of the small 1/4-inch pins. These pins are uninsulated, so when you're sticking them into wood, they're measuring the moisture content all along these pins, and then giving you a readout of the greatest moisture content reading that these pins have encountered. Otherwise, if you're using the longer pins, these are insulated pins, and they're only uninsulated right at the tip. So you can drive them into a wood timber and then get various readouts along the way of exactly where this pin end is in the timber. So it's not taking readings along the whole length. It's just taking readings at the tip. Along with this, it's important to realize that there are pin correction factors for insulated versus or non-insulated versus insulated pins. There's temperature correction factors, and there's also a species correction factor. So this basic moisture meter is usually set up for Douglas fir. So if you're on the East Coast and you're working a lot with pine, there's a correction table to go to. Likewise, if you're poking your moisture meter into OSB or plywood, there's also a species correction factor for those. So back to our terminology in this concept of equilibrium, wood in equilibrium. Here's an example of why this is so important. Say, for example, we're in California, around Los Angeles. It's July, and we have we're expecting wood in service, so like siding on the exterior side of the building, to be averaging 15% moisture content. When we come back in December, we should be seeing lower readings. But that difference between 15% and 12% means that our wood will have changed in size during those months. So this is just a reminder that you can always expect wood to be on the move. Likewise, there's some key wood changes properties based on its defects, and some of these defects are things like knots. Here's a knot in a connection. You know, when they sent this material to the site, they didn't know where the connection would be. So if you see a connection through a strength-reducing property, it's really important to let the engineer know that it's there, because knots and slope of grain and checks through the wood reduce the strength of wood dramatically. And here's an example of what slope of grain, a dramatic slope of grain, looks like in service. You can see these long checks. So it's a really high slope of grain, and it means that this material, whether it was graded or not graded prior to its installation, means that it's a very weak member. And so you can see that without having to do a lot of calculation. You see a steep slope of grain, you know that you've got a weak member. Or you see large knots in the face of material. Those are definitely strength-reducing properties. And maybe it wouldn't be a big deal if it wasn't loaded. That could be perfectly acceptable. This member could have perfectly acceptable strength, but because of where it's loaded, it no longer meets the criteria. This is easier to see in a historic property. So that brings us to in situ stress grading. We've had really good luck with this. In situ stress grading is a really powerful tool. We've used it where wood elements are going to be affected by maybe a change of use or some added loads, and where strengthening would be really expensive, and you could avoid it if you had a slightly higher flexural strength, and you can individually grade a member for that. Or for in historic properties, much of this material may not be grade stamped, so your engineer is going to need to know how strong to expect this material to be, and if you can grade it in this way using ASTM D245. And ASTM D245 is all based on those strength-reducing properties that we've talked about: knot size, species, the wood defects in their location, the slope of grain. And I'll give you an example of, this is a table that we've developed in-house. If we're looking at it a little bit closer, you can see it has all those same things. What's the moisture content of the wood when we were there? What's the slope of grain that we saw? Where are the knots, and how big are they? And that table will give us allowable properties that we can use in our subsequent calculations. So now that we've talked a little bit about dimensional stability and how moisture impacts wood, let's talk about how wood deteriorates. Wood deteriorates in two main ways: through biological agents and non-biological agents. And we don't have time to cover everything today, but I do want to focus on decay fungi, or rot, and insects. So decay fungi, it sounds really scary, right? And it is the #1 contributor to in-service wood damage. Millions of dollars a year are caused by fungal decay. But it's really hard to control, right? Because fungal spores, they're everywhere. They find a suitable surface, usually wet wood, and then they germinate, and they grow hyphae, mycelia mats, and then they start attacking the wood, boring through those cell walls, and then they release enzymes, and the wood becomes rotted, and then they might form those mushrooms. They're called fruiting bodies. And then they're going to just start releasing spores again. And so the cycle of life continues. But it's really important to understand that not all fungi cause the destruction of wood matter. For example, mold fungi is a surface phenomenon, and your wood might be moldy, but that doesn't necessarily mean that it has decay fungi. And decay fungi are the ones that are eating through wood. So if we look at decay fungi and how they attack, hopefully that we can understand the potential for damage and how to prevent it. So it's important to understand the conditions necessary for fungal attack. And these are temperature, oxygen, moisture, and a food source. And if you prevent one of them, then the potential for the attack diminishes. But understanding that it's really hard to control things like oxygen or food source, so you're really working with temperature and moisture. But wood rot fungi really like the same kind of temperatures that we like. So we're down to controlling the moisture. So if we can keep wood dry, we won't have attack by fungal decay. So once fungal decay occurs, then it becomes really difficult for us, not only to find it and to understand the structural loss that we're getting, but to really understand the extent of that loss. And that really deals with incipient decay. So that means that the hyphae are already doing their work, but incipient decay is decay that you can't see visually. You can only see under the microscope. And we'll talk more about that in a little bit. But decay falls into three main categories, and it's brown rot, white rot, and soft rot. So if you ever hear someone using the term dry rot, that's a misnomer. And please don't ever use that term. It'd be analogous to how it grates on the nerves of a conservator to hear somebody misuse preservation versus rehabilitation. It's just a misnomer. Rot is always going to need those things that we've talked about. It's always going to need moisture. And so there are fungi that are considered true dry rot because they are water-conducting fungi. There's a species of a brown rot that creates a rhizomorph. It looks like a root structure that is helping it carry water. But it still likes damp wood, and it will still move best through damp wood. So brown rot looks like this. Brown rot is characterized by these, the cellulose is removed, and there's cracks across the grain. It becomes really brown and collapses easily. And you're mostly going to find it in softwoods, which is why we see it in construction so often, because we're mostly using softwoods. And white rot is characterized by the removal of cellulose and lignin. Lignin is brown in color, and so when it's removed, that's why it looks whiter. It's sort of spongy and fibrous in appearance. And the third type of rot is soft rot, and we don't see it often in structural members, mostly because it's related to molds, and it's we'll see it in piles particularly. So back to incipient decay. Here's a photo. Obviously, this is not a historic structure, but I think it's interesting because they've shored this rotten wood beam right here. But how did they know to stop shoring it here versus, say, here? And this all has to do with incipient decay. So this is obviously visually rotted. It's lost a lot of its strength. But what's happening right here? So the Wood Handbook, which I like to refer to as the Wood Bible, it's produced by the USDA Forest Products Laboratory, and you can read it online for free or purchase it. It's a great resource to have. The Wood Handbook says that by the time weight losses resulting from decay have reached 10%, most strength losses may be expected to exceed 50%. So at weight losses of 10% or less, decay is detectable only microscopically. So you would never know visually that you've lost 50% of your strength. That's pretty scary. This is what it looks like under the microscope. This is that visual decay you wouldn't have needed a microscope for. You can see how it's really destroyed the cell walls. This is incipient decay under the microscope. You can see this fungal hyphae has started chewing through these cell walls. And so you've lost a lot of strength right here. And you would never know it in service. So there's this basic rule of thumb that says that you need to take out whatever your decay surface is that you can visually see, plus 24 inches on either side. Well, with a beam or a column in service, that really means that you're replacing a lot of wood materials. And there's nothing that strikes fear into the hearts of conservators more than taking out more than they need to. So if you go back to the research and look and see where is this line of incipient decay, where does it really end, the research is suggesting that in some species it's as small as 5 inches. So we have this knowledge gap between our rules of thumb that we use often in construction and what the research says. And then plus what we want to do as conservators and be as gentle to this material as possible. So what does this mean? We can either remove it and basically remove the member in service, or we can start looking at ways to treat it. So first we have to stop the moisture source, remove and treat the decayed area, and then determine this plan. And realizing whatever your treatment plan is, as the engineer, you cannot rely on the decayed area for your connection detailing. So that's why a lot of, and we'll talk about this later too, why a lot of the connection details look so bulky to us, because we can't rely on that wood because of incipient decay. So here's a quick and dirty method we can use in the field to start thinking more about incipient decay or decay in general. It's called the Pic Test, and you poke a sharp instrument like an awl into the wood and pry upwards, and if the wood fails splintery adjacent to the tool, then you probably have good wood. If the wood has a brash failure immediately adjacent to the tool, then you probably have decayed wood, as if this mycelium mat wasn't giving you enough visual clues. So another great way to look at and see if there's hidden decay is using some what's considered non-destructive tool. This is a resistograph. What it is a micro drill. Despite the large size of the equipment here, it's a very small drill bit drilling into wood and in real time giving you a graph of the resistance that drill bit is encountering. If the reading on the graph that you're doing in service, if the reading drops and stays at 0 for a while, then you know you have some sort of cavity. Was that zero resistance made by decay, or was it made by an insect gallery, or was it made by a check? You don't have all of that information, but at least you have some information that you can start mapping where those suspect areas are, where those decay pockets might be, where there's areas of low resistance, and get a better understanding of what's going on inside that timber. So that leads us to deterioration by insects. And the most popular, of course, wood-destroying insect in the United States is termites. We have a lot of problems with termites here in California. The two main species of termites that we deal with in California are Drywood termites and subterranean termites. Here's a photo of some subterranean termites. You might recognize them because of their pale little bodies. And subterraneans are characterized that they can't be exposed to UV. They'll desiccate. So they build these shelter tubes out of mud and earth, and they'll build them up your concrete wall and get into the wood foundation that way. So subterraneans, they're building their nests in the earth, and whereas drywood termites, their nests are elsewhere, and they don't mind being exposed to UV. So so they don't build those shelter tubes. You might just find insect galleries, these termite galleries, in random places. Both species of termite, drywood or subterranean, at certain points in their life cycle, some of them grow wings. This is a photo of Formosan termites that are really taking over New Orleans in the south, swarming at their life cycle where they have wings, and moving off to find new colonies to destroy more wood. Here's a case study, why it's so important to have your hands on wood if you can access it. In this particular example, this wood, it doesn't look bad, right? But the minute I poked at it, it fell apart, and you could see underlying all of the termite galleries inside of it. And the great thing about termite galleries is that they usually contain some sort of frass. Termite frass is a polite way of saying termite poop. And their frass is identifiable to the species. So this is characterized, these ridges are characterized by drywood termites. And it's just really nice to be able to tell your owner that you are suspecting you have an infestation of subterranean versus drywood termites, because the treatment plans are going to be different. Here's another case study of some exposed wood columns that had a really decorative element overlaid on the wood columns with some masonite panels and some mirrored glass. We got permission after we started noticing these little tiny holes. We got permission to take out some of this masonite and mirrored glass, and out came a bunch of termite frass. And again, we've got drywood termites in this particular instance. And this is a really nice place for us to be able to use the resistograph again to check how much column we have left. And maybe even the resistograph can tell us a little bit more about the composition of that column. In this case, we had such a large drop in resistance that we suddenly understood we weren't dealing with a solid column, we were dealing with a composite column. So some of the other wood-destroying insects are beetles. Beetles are more prevalent in Europe than they are over here, but we do have them. This frass on the left and versus the frass on the right, it feels a lot like sawdust. And so this is powder post beetle versus death watch beetle, which is a little bit grainier. And beetles are often characterized by these teeny tiny little kick-out holes. Beetles really like their galleries to be clean. And so if you're seeing piles of frass anywhere, then you've probably got kick-out holes where they're emptying their garbage. Other wood-destroying insects, carpenter ants, they just look like a really big rendition of the regular garden variety ant, or carpenter bees, which are a bigger version. They're almost all black, and so they're really visible versus honeybees that are much smaller and striped. And here's a case study. Not long after I started working as an engineer, I was doing a condition survey at a winery and noticing there was some paint missing from this ridge line and marking that down. But as I was standing there, I happened to look through my binoculars at it more closely, and as I was doing that, I noticed that there were insects coming in and out of it. So it wasn't missing paint, it was actually a hole, and the insects that were flying by me by that time were carpenter bees. So just another reason to look at things longer than maybe you think you need to. Often my colleagues will come back and just give me a photograph of something that they've seen on site and been curious about. My colleague brought me back this photo and was very curious, and it turns out that it's ants that were moving all of their ant eggs and from a wet location to a drier location. So just seeing this pile of ant eggs, you know that somewhere there's a leak that we need to address before it becomes a bigger problem. So we've talked about some of the biological agents that deteriorate wood. Let's talk a little bit about non-biological deterioration, and in particularly weathering. We see a lot of weathering on those durable historic structures. How do we deal with it? What is it? The weathering process happens when wood is exposed, whether it's exposed to heat or water or UV light or some sort of mechanical abrasion or all of the above. It's going to start the weathering process. And usually that starts with photodegradation, UV light, and then microscopic changes start happening at the cellular level and grow to become warping or checking and splitting. And then the wood starts to erode and exposing more wood, and the cycle continues. The best news about the weathering process is that it's also a surface phenomenon. So often you can simply sand away that first layer and expose really good wood behind it. And then, of course, that wood needs to be protected from further process. So what does this look like? Here's an example of shingles that have been fairly newly added to this building, and you can tell because they're nice and dark and brown versus the older shingles on the building that are grayer. All unprotected wood is going to gray or silver to this level. That's the photodegradation process that started from UV. In this case, it didn't take too long for photodegradation plus water washing over the surface to also change the appearance of the shingles. This is a photograph from my house where I started looking at these wood shingles and thinking more about those raised edges that we see. We talked earlier in the presentation about early wood bands and late wood bands. And this is just another example of how late wood bands are, in effect, more durable. They're denser than the early wood bands. And so over time in this weathering process, as this has started to erode with water and photodegradation, but the denser bands have remained raised. So we get that rippled appearance. So a little bit about the difference between decay and weathering. So weathering, again, is that surface phenomenon, and decay requires a decay fungi and a moisture source. And so here's a little fruiting body that's telling us that we have decay. It's often characterized by that sort of sunken appearance in the paint finish there. Or decay, we've got those cubicle checking, and it's gotten darker brown as opposed to that silvery gray of weathering. This is an example where the house was covered in shingles, and so the original shingles had been exposed, and you see they had lost some section over their time of being weathered. But once they were covered with these white shingles up at the top, the weathering process was in effect halted, remained in place. Case study on weathering. This church in Los Angeles, only the top portion of it is wood. If we look at it up close, we see that the paint finish on the wood is starting to fail, and wherever it's failed, we're starting to get that gray, silvery appearance. That's step one in the weathering process. And then another example, these balusters, they looked in fairly good condition until we touched them, and they completely moved. So you can see this, the paint finish is deteriorating, and we're starting the weathering process, but we've also been exposed to some decay. We've lost the connection here. So more than one thing is happening at a time. It's often the case, right? In this case, at the winery, there's some weathering going on at the base of the columns in the winery. And just over the process of our investigation, we could watch the weathering process happen. You see this heavy deterioration at the base of the column. Well, we could watch it happen because every afternoon they would come in and they would clean the floor with a high pressure, high temperature water spray, and that was just physically, mechanically eroding the surface of the wood. So we could recommend to them a gentler means of cleaning their floor. Another interesting case study of weathering happens in a microclimate. In this picture, imagine that you're sitting in the ocean, and this screen door is right in front of you. So the ocean spray is quite available to this wood screen. So when we used the moisture meter on it, it was dry wood, dry to the touch, but it was giving us really high moisture content readings. And that's characterized by the salt content of the wood, salt degradation. Over time, this is what happens with salt attack. After the moisture dries out from the wood, the salt crystals are left behind, and those salt crystals break the cell walls, and so the wood becomes fibrous, well-looking. So let's go back to our themes. We've covered a lot about wood and how it's related to moisture and how it deteriorates in the presence of moisture and insects and weathering. And now let's talk a little bit more about our conservation strategy in our remaining time. So I just wrote down some questions that I ask myself as an engineer that I need to develop more answers to with the owner in concert with the conservation professional. And these questions are things like, will this wood member be kept in its original location? Do you care about this wood member? Is intrinsic to the value of the property. Is the site going to change? Has it changed in the past? Maybe, for instance, maybe there was really tall trees in front of the structure, but some event caused those trees to be taken away, and now we've got more exposed wood than we would have had in the past. We're measuring on site how thick the wood member is now, and that tells us a little story about maybe how thick it was at one point. Is the condition that the wood is in now, is it going to keep it from functioning in the condition that you're going to be using it in? And will the aesthetic be changing? Often it's not, right? I mean, we don't really see that in historic conservation, where you're changing from painted to natural or natural to painted. But it could happen. So with that, there are protective treatments to consider. Film forming or penetrating. The film forming are those paints and varnishes. The penetrating protective treatments are things like water repellents and semi-transparent stains, and also preservatives. And so in the time that we have left, we'll talk a little bit about the types of preservatives that we have available to us. The first type are pressure treatment preservatives, and these are used in a factory setting. You wouldn't use these on site yourself. But this is a Douglas fir sample. Douglas fir is really difficult to treat with preservative, and so they have to incise it. There are little poke holes throughout this piece of material, and then the treatment is pressurized and driven into the wood cell walls. And you can see in this cross-section that it doesn't go in very far. So this section of wood remains untreated and vulnerable. The other type of preservative available to us deal with non-pressure treatment or field treatments. These are diffusible or coatings or fumigants. Some of these diffusible preservatives are like these boron rods, and boron is water soluble. So whenever water touches it, the preservative begins to leach out, hopefully into the wood, protecting your wood. But over time, you've lost the protection because it is water soluble. Another type, these fumigants, they come in little packages, or coatings. And they don't go very deep into the wood either, especially not with pressure treatment. So when we're dealing with the repair and rehabilitation of existing wood structures, sometimes we're dealing with repair of past repairs. For instance, on this picture on the left, the repair was to add a sistered member, but obviously the moisture source was not stopped, and this new sistered member has begun to decay. In the example on the right, these wood infill floors, someone didn't strengthen or support the end of this purlin. So this repair has to be repaired. So strengthening of existing structures usually deal with adding new connection elements to strengthen them, which they're rather unsightly. So it's a matter of working with the conservator and the owner to figure out the best way to strengthen the material. And at least we know how the structure is going to be loaded in service, and we can plan accordingly. and then to do some sistering elements and to stop the decay from occurring on those sistering elements, so we're not forced with or faced with dealing with, say, large steel beams in place of original wood members. So you can count on whatever rehabilitation measure that you're doing. You can count on some load sharing, some load jacking, and the engineer is going to want to understand the interaction between the structure and the strengthening elements. So it's really important to know what's going on in this wood so that we know how this new material is going to react with it. So in summary, our takeaways from today are that the dimensional stability and moisture movement in wood happens in 3 directions in the presence of moisture, and it has significant structural and architectural implications. For biodeterioration, we've learned that wood deteriorating fungi in the presence of moisture also has structural implications, especially when you're dealing with incipient decay. So decay that you can't see, but it's there and impacting the structural strength of your material. And then for structural assessment, we learned a little bit about in situ grading and how it's dependent on observing and accounting for those natural strength-reducing characteristics, such as knots and splits and slope of grain. And then we looked a little bit at the conservation strategy, and the main takeaway is that we have to address the underlying causes and not just the symptoms, and we want to do it with the gentlest means possible. So, in conclusion, if we have a wood historic structure, that wood is obviously telling us a story, but its condition is going to determine its future, and we know that wood can be durable, but it is subject to degradation from physical, mechanical, and all kinds of other agents of deterioration. And once that deterioration has started, then it's susceptible to other means of degradation. So the same conditions that attract fungal decay are going to attract those insects as well. So we want to address what caused the wood to deteriorate and what can be done to repair it, and ask those questions. Is it going to be reused structurally, aesthetically, or are we keeping the wood for purpose of authenticity? And just to conclude, of course, here's my contact information, but there's some other really great resources out there. Like I mentioned, the Wood Handbook found at the Forest Products Laboratory through the USDA website. NCPTT has a really great resource. Stan LaBelle out of the Forest Products Lab and Ron Anthony have put together a really great resource on using preservatives in historic structures, and I can recommend their report to you. And then, of course, the Interior Secretary's standards are up on nps.gov. Thanks so much for your time today, and I'd be happy to take any questions.
Thank you, Janelle. We don't have any questions at this time, so if you do have questions, send them in here quickly before we conclude. If you think of a question after this program, please forward your questions to either us at CPF or to Janelle directly to get your answers to any questions you may have. We want to thank you again for joining us today. You will receive an email with a link to a survey and a link to a PDF copy of this presentation. We would appreciate any feedback on this webinar and recommendations for future topics. This is very important to us as we plan our educational program for next year. If you're not a member of the California Preservation Foundation, we would encourage you to join as an individual a nonprofit, government, or a corporate member. Each member receives benefits including discounts to all programs such as our webinars, workshops, conference, and awards program, members-only tours. Your attendance at this program helps us fulfill our mission to provide leadership to protect California's historic sites and communities through advocacy and education. Membership information is available on our website. And I'd like to remind our attendees that we do have a couple of special events coming up. On Friday, September 27th, is the California Preservation Awards. They'll be held at the Merchants Exchange Building in San Francisco. It's a dinner, reception, and awards presentation, and it will also celebrate the 30th anniversary of the Preservation Design Awards, and will include a very special event, and that is the release of a new book that was written about the Preservation Design Awards program by J.K. Deneen and with a foreword by John King, published by Heyday. We have information about this book on our website, and we'd encourage you to take a look and to support Heyday by purchasing the book. We also have a very special tour coming up of the Oliver Ranch, and that'll be October 26th. It's a Saturday, and you can get information at the Oliver Ranch Foundation. We'll be putting information about that tour up on our website. It's a very special event led by Stephen Oliver, who is the former president of the board of the San Francisco Museum of Modern Art. So, if there are no other questions, I'd like to thank Janelle Leafblad for the outstanding presentation. And once again, thank you for supporting us, and I hope you have a very good afternoon. Thank you.